Okay, this video here, this one here is about limits at infinity. So what we're going to do is let x get very, very big or very, very small. So this is the typical situation that we're going to investigate in this lesson. If we're taking a limit at infinity, then that means we're letting x get big, and we ask ourselves, what's happening to the function, right? So does the function approach a number as x gets big, or does it not? In pretty much the same vein, right, you can ask the question going in the other direction. So if you have a function like h of x, you're saying we're going to let x travel to negative infinity in this direction and ask ourselves, does the function have a limit, right? Is it approaching some number? Okay, so we'll do the norm here and just take a look at an example, and we'll just do this empirically, right, with some data just to see what things look like. So here's a pretty typical function, y equals 4x squared over x squared plus 2, and we're going to ask ourselves this question, right? We're going to let x get very, very big, or let x get very, very small, but still in the infinite sense. And we're going to say, what happens to y, right? What happens to the function? Okay, so we can look at a table, right? Because this is the way that we have done this kind of thing. So if you want to say what's going to happen as x gets very, very big, then notice the table here looks a little bit different, because what we want to do is to just try some numbers, but we want to look and see what happens to the function for large values of x. So if you look at the second column, you can see the numbers start out around 1 and 3, and then they settle down pretty close to 4. So it appears that this table, as x gets bigger and bigger, y seems to be approaching 4. Okay? And if we look in the other direction, as x travels to negative infinity, so now we look down here and we're traveling in this direction, so these numbers are getting bigger and bigger but in the negative sense, then the same kind of pattern can be seen going in this direction. So the y values start out around 1, 3.5, and then they settle in, right, very, very close to 4. So the idea here is, as x gets big, y approaches 4. As x goes to negative infinity, y also approaches 4. So we can write down those two statements and then talk about that. So for this very example here, right, the limit of f of x as x gets very big, from the table, that appears to be 4. And pretty much the same thing happens going the other way. So we can make this statement here. So it still agrees with our earlier idea of a limit. These values, right, you're seeing numbers very, very close to 4 as x approaches something. Okay, something you might recall from algebra class, is that when you have this kind of phenomenon occur, then something graphically is occurring at this point, right, when y is equal to 4. So what we would say here is we have a horizontal asymptote. So we have a horizontal asymptote here at y equals 4. Because if you try to imagine this, x is getting big and the function is settling down around 4. So what we can really see is that the y values are very, very close to 4, and the graph of this function is starting to look like a horizontal line. Hence the horizontal asymptote, right, at y equals 4. So we can put a picture of this up. So I won't really plot any points, I'll just do a rough sketch here. Okay, but what we can already tell here is that we're going to have this horizontal asymptote here. This is going to occur at y equals 4. And then the graph, right, if you plot a few points, you're going to see this kind of phenomenon here. And a reflection on the other side. Okay? So this is the idea. If you plot this function, you're going to see this kind of phenomenon. If your eyes look over here, as x gets very, very big, the function values are really close to 4. As x gets very, very small, negative infinity, the y values are also going to 4. So this idea of approaching infinity or negative infinity and having a limit leads directly to a horizontal asymptote to the graph. Alright, so one of the other things, really big things to talk about here are these two special statements here. And these we use all of the time in this section, and the nice thing about these is they're very, very intuitive. Right? So you can just think of plugging in concrete numbers and you can see why these statements are true. I tend to lean on this second one here, because if you look at the statement, x is getting very, very big, right? So you can imagine here downstairs, right? This here is for positive n, so we should note that here. So n is positive, right? So we have positive numbers. So you can imagine things like 1 over x cubed. And so if x is very, very big, the bottom part of this function is going to grow without bound. And then if you take the reciprocal of that, 1 over something large is getting smaller and smaller in size, right? And hence we get this limit of 0. So the analogous thing happens here, right? You have the same kind of expression, n is still positive, x is going to negative infinity. So the magnitude of the denominator expression is still quite large, and 1 over that is going to get smaller and smaller. So these are very versatile statements, and they show up in all types of different scenarios. Alright, so the last thing I want to do is just to revisit our earlier problem. So we'll take a look at this again and make this the center of attention. Because the way that we justified a horizontal asymptote here was by looking at a table and saying that the limit of this function as x gets big is going to be 4. But with the new tools, now we can make this a little bit clearer, right, and see how this works. So I'm going to try to take the limit here, limit as x gets big of this function, 4x squared over x squared plus 2. So the way that you can visualize this is we can manipulate this expression. So what I'm going to do is to divide out x squared on the top and also the bottom. And what that's going to mean is that you're going to take the top expression, divide it by x squared, do the same thing here in the denominator, and then just do some algebra. Okay, so I'm going to make some space here. So upstairs we're going to have 4x squared and then divided by x squared. And then in the denominator we're going to have x squared over x squared, right? And a similar thing here, plus 2 over x squared. Okay, so we're just manipulating this expression to see what we've got. And notice we have a little bit of simplification, right? You just have a 4 here, and this here will transform to 1. So I'll take this up here to finish up the problem, right, to see what happens. So then this is the limit as x gets very big, right? So we have 4, and then we have 1 plus 2 over x squared. Okay, so this is the expression here. So now if you take a look at this, the important part of this is that earlier limit that we saw. So I'll put this right up here so we can remind ourselves, right? So as x gets very, very big, if you see the reciprocal of something large, that means that this part of the limit is going to tend or go off to 0. So that part can be detected in this problem right here. So 2 over x squared, as x gets very, very big, this part is going to be negligible, right, and it's going to tend to 0. So then if you take a look at this limit, okay, everything else is unaffected by x, the movement of x. So you end up with 4 over 1 plus 0, and this simplifies to 4. Okay, and you can guess that this 4 corresponds to the same value that we had before, y equaling 4. So this is the way that you can justify, right, that this function here, the 4x squared over x squared plus 2, has a horizontal asymptote when y equals 4.